Bühler Motor fractional horsepower DC motors. Application engineering. Hello, my name is Gerhard Hofmann. The second part of the training session concerning application engineering will show you how the existing motor we selected must be modified to meet the exact specification values for the load point in the application. In the first training session, we learned how to find an existing motor out of our portfolio that can meet the customer requirements in terms of load speed N sub L at a certain load torque T sub L. The additional knowledge of the operating conditions for the motor allowed us to create a performance curve that describes the motor we need. We remember how a performance curve of a permanent magnet DC motor generally looks like. It's a couple of curves which describe the behavior of the motor related to the torque load applied to the motor. For the following calculations, we will do an assumption which is valid for the size of motors we are dealing with. We simply neglect the losses inside the motor and set the ideal no-load speed N sub 0 ideal equal to the no-load speed N sub 0. The efficiency and power curves are also not necessary for the next calculations and will therefore be omitted. By looking at the two straight lines representing the speed torque and the current torque curve of the motor, including the load point at T sub L, we see the target curves we want to achieve with our selected motor. If we now show the speed torque curve of the selected motor, which is our basis, we can indicate its no-load speed N sub 0 basis and stall torque T sub S basis. The same for the current torque curve, which indicates the stall current I sub S basis. Concentrating on the speed torque curve, we can see two parallel straight lines. How can the dotted line, representing the existing base motor, be shifted to meet the target line? To answer this question, the armature of the motor has to be examined a little closer. We see here a cross-section and a top view of a wound armature. Each gap contains a number of copper wires which fill the gap to a certain extent. The cross-sectional area the copper wires are covering is called copper filling A sub Cu. A sub Cu can be calculated by the number of turns per coil N and the wire diameter D with the following formula. A sub Cu is D square times P divided by 4 multiplied by the number of turns N. For each basic motor, this factor A sub Cu is to be considered as a constant. It is a maximum value, as for space reasons there cannot be more copper applied. Less would be possible, but does not make sense, as the motor would become weaker and less efficient. Now the number of turns per coil for the target motor can be calculated. Basis is the existing motor with its number of turns N sub basis and its no-load speed N0 basis. For the new motor, we know the no-load speed N0 calculated, and we want to know the number of turns per coil N sub calculated. As there is a reverse proportional relationship between the no-load speed and the number of turns per coil, the calculation looks as following. The number of turns for our calculated motor N sub calc is the number of turns of our basis motor N sub basis multiplied by the no-load speed of our basis motor N sub 0 basis divided by N sub 0 calculated. After the calculation of the number of turns N sub calculated, we can calculate the new wire diameter. Using the copper filling A sub Cu, which is the wire diameter of our basis motor D square multiplied by P divided by 4 multiplied by the number of turns of our basis motor N basis. Assuming that A sub Cu is constant and the new number of turns is N sub calculated, the formula can be changed to read D, which is the new diameter of our new calculated winding, D sub calc, is the square root out of 4 times our copper filling A sub Cu divided by P multiplied by the number of turns of our calculated motor N sub calculated. Remember, the assumption made was a constant copper filling A sub Cu. As A sub Cu is identical to the basic motor, also the speed regulation constant R sub m is identical to the basic, and this means the speed torque curves are parallel. Finally, the new torque constant K sub t can be calculated. Again, we have the existing motor as basis with its number of turns per coil N sub basis, and its torque constant Kt basis. For the new motor, we know the number of turns N sub calculated based on a direct proportional relationship between Kt and the number of turns per coil. The calculation looks as following. K sub t calc of our new motor, of our calculated motor, is K sub t of our basis motor multiplied by the number of turns of our calculated motor divided by the number of turns of our basis motor. A new motor is now defined, which meets the load point requirements N sub L at T sub L for a specified voltage. Samples could be built using components from the existing motor. The only difference would be the new armature winding based on the calculation. A much quicker way of getting motors that meet the load point is using the existing motor and operate it at a different voltage. From the basic motor theory, we know that no-load speed is directly proportional to supply voltage. This relationship is shown here. No-load speed N sub 0 at voltage V1 divided by N sub 0 at voltage V2 is voltage V1 divided by voltage V2. Looking at a set of speed torque curves, this voltage dependency can be shown by parallel straight lines where voltage 1 is smaller than voltage 2, which is smaller than voltage 3. The necessary voltage to achieve a required no-load speed N sub 0 calculated of the motor can be calculated as follows. Calculated voltage V calculated is our voltage of the basis motor V basis multiplied by no-load speed of the calculated motor N sub 0 calculated divided by N sub 0 basis. If there is a chance to adjust the voltage in the application, it is possible to use the already existing motor as it is. The motor is available and no samples with specific armature windings have to be made. I'm coming back to the practical example that I started with in session 1. Here is the performance curve of the motor we need. The target motor that we are aiming for needs to have a no-load speed, which is a no-load speed calculated, of 5,630 RPM. We want to know the numbers of turns per coil, N subcalc, and we also want to know the wire diameter, D subcalc, for this new target motor. The motor that we have selected out of our portfolio was the 113044236 with a no-load speed of 4,100 RPM, 30 turns per coil, 0.375 mm wire diameter, and the motor has a KT of 5.3 Newton centimeters per amp. For this motor, we can now calculate the copper filling, which is 3.31 square millimeters. We also know that this copper constant is a constant, so the filling of our target motor should be identical. We calculate now the number of turns per coil for our target motor. Its number of turns calculated equals our numbers of turns of the basis motor multiplied by the no-load speed of the basis motor divided by the no-load speed of our calculated motor. And in our case, the result would be 21.85. But as only integer values can appear for the number of turns per coil, we have to round this up to 22 turns per coil. Calculating the new wire diameter now means the new wire diameter is D subcalc is the square root out of 4 times our copper filling divided by P multiplied by the number of turns that we have calculated. And the result of this calculation would be 0.437 millimeter. But as we can only use standard wire diameters, we have to look up what is the next closest wire diameter in the standard range. In this case, it would be 0.425 millimeters. In order to be safe concerning the copper filling, the next smaller wire diameter should be used. Last but not least, we calculate the new torque constant with the formula K sub T calculated is K sub T basis multiplied by the number of turns of the calculated motor divided by the number of turns of the basis motor. And in our case, it's 5.3 Newton centimeter per amps multiplied by 22 divided by 30, which results in a new KT of 3.89 Newton centimeters per amp. A new motor is now defined that will meet the custom requirements at the specified voltage. If we want to see how we can meet the load point by modifying the voltage instead of the armature winding, we can look at the no-load speed of the calculated motor, so the target no-load speed, which is 5,630 RPM. Our selected motor, 113044236, has a no-load speed of 4,100 RPM at 24 volts. And with this calculation, new voltage, which is Vcalc, is the basis, the voltage of our selected motor, multiplied by the no-load speed of the calculated motor divided by the no-load speed of the basis motor, and this results in a voltage of 32.95. So in other words, the required load point can also be reached operating the 113.044.236 motor at a voltage of 32.95 volts. Based on an existing motor, either operated with a different voltage or modified by a different winding in the armature, we can achieve the goal of operating optimal at a defined load point. The next session deals with the use of gear motors together with the motor.